Hello, and welcome to our ELECOMP Capstone 2023 Fall Symposium video presentation. We are Team Amelia, and our project is the wireless enablement of green power technologies for edge devices, which has been nicknamed Project Amelia. Here are our technical directors, Joe Morera, an engineering fellow, and Bradley Willard, an engineering manager, both from Zebra Technologies. They have provided us much support and guidance throughout the project. For our yearly comp capstone designers, we have a total of 7. 3 computer engineers, which are Andrew O, Alan Liu, and Eddie Perez. We have 3 electrical engineers, which are Alan Polanski, Lucas Frost, and myself, Joseph Dyer. Nick Fedorenko is our double major, majoring in both computer and electrical engineering. Our sponsoring company, Zebra Technologies, was founded in 1969 and offers global computer printing technologies. Zebra specializes in printers and various other technologies used for marking and tracking. Their products can be found in several diverse industries such as retail, healthcare, and many more. The motivation for this project is to maximize the green energy usage in Zebra devices. Zebra devices, such as printers, incorporate a battery to power the device. These batteries must be recharged, and the scope of Project Amelia is to recharge these batteries when the renewable energy at a power grid is at its maximum. In doing this, we will reduce the carbon footprint of Zebra devices and their consumers, as well as reduce the electricity costs for Zebra customers. This creation will help push Zebra towards a leading company of green energy. The anticipated best outcome of this project is to create a subsystem that predicts the optimal time to charge the battery, that being when the renewable energy is at a maximum. The subsystem itself will require power, therefore we look to minimize the total power consumption of the subsystem so that the majority of the green energy will be used to recharge the battery. The subsystem will incorporate a dual Wi-Fi Bluetooth based architecture as well as a user dashboard to provide user information such as the current green energy ratio from the grid and the total power consumed. We aim to conclude the project with a test fixture that reaches the pre-engineering validation testing levels. At this time, the team's accomplishments are the selection of the power measurement method as well as the voltage regulator. A plan has been derived to minimize the total power consumption of the subsystem. A selection for the microcontroller that includes an internal Bluetooth system. We will utilize a Bluetooth Low Energy service. Non-volatile memory is utilized to hold the data of the subsystem, and a cloud server connection that will run the majority of the software that controls the subsystem. There will be a Wi-Fi transceiver that will connect the subsystem to the cloud server. The integration of this system to Zebra devices will make them more environmentally friendly, which will appease to several Zebra consumers, as well as new consumers. Consumers will also avoid the economic activity of non-renewable energy sources, such as increased cost of fossil fuels and/or coal. These integrated devices will reduce the customer's total cost of ownership, therefore bringing in new Zebra customers. Here, you can see a block diagram that summarizes the Amelia subsystem. Squared in red is the portion that I have worked on, which is the power input of the subsystem. My name is Joseph Dyer, and I worked on the selection of the power measurement method as well as the voltage regulator. I derived a plan that will minimize the power consumption of the subsystem. I'm also the lead designer in the creation of the hardware schematics. For the power supply measurement, we will utilize a chip to measure the power input to the battery. As you can see, with the use of a power delivery controller, we will recharge the battery utilizing voltage range of 5 to 20 volts and a current ranging from 1 and 3 amps. The measurement chip will collect this data and transmit it to the microcontroller for further processing. We look to minimize the power consumption of the subsystem. During the active mode, which is when the battery is being charged, the subsystem will be fully functional to provide the user constant data of the charging time period. But during the standby mode, which is when the battery is not being charged, the subsystem will transfer into a sleep mode. This mode is a low power mode, where the subsystem will wait for the next charging time period. During the standby mode, the subsystem will perform quick interval bursts to check in on the battery. The voltage regulator will take a portion of the supply power to power the subsystem, which is 3.3 volts. It is important that this regulator utilizes the least amount of power from the supply, so that all the green energy that is coming in goes to the battery and not to power the subsystem. To do this, the voltage regulator must have a high efficiency rating and a low quiescent current draw.
Hi, I'm Alan. I'm an electrical engineering major. I worked on the power system subsection of this project. That involved current and voltage measurement and choosing a voltage regulator. To a lesser extent, I also researched power grids and I also helped research microcontrollers to choose a suitable one for this project. I spent most of my time on current measurement. One of the three methods we thought were suitable for this project was the shunt resistor. It's a resistor which you measure voltage across and use Ohm's law to determine the current through it. It is a high precision method and is relatively simple to implement, but on the other hand, the resistor can cause power losses. There were two contactless sensors that we thought would be a good fit for this project. One was the Hall effect sensor, the other one was tunnel magnetoresistance, or TMR for short. Both measure current by using its magnetic field. Pros for the TMR sensor include that it's higher precision than the Hall effect sensor and that it's not actually in line with the current source. Unfortunately, both the Hall effect sensor and the TMR sensor are susceptible to magnetic noise. Both are less sensitive than the shunt resistor, and both required additional interfacing with a separate analog to digital converter for our microcontroller. This is our testing setup for the different ICs that we're trying out. The power supply provided current to be measured, and it went into our evaluation boards, and then we read the output signal from the evaluation boards using an oscilloscope to determine the quality of the signal and how much noise there was interfering with it. In the end, following testing, we immediately eliminated the TMR sensor due to it providing too weak of a signal to be useful. That left the Hall effect and shunt resistor sensors. For this, to determine the winner, we decided to see how much power they consumed. And in the range of our project, the shunt resistor ended up consuming the least amount of power, since our project only uses 100 milliamperes during sleep mode, and when it's active, it will only use up to 3 amps.
So I'm Lucas Frost, and I'm an electrical engineer. I mostly worked in grid data and on the cloud for this project. So I was tasked with conducting research on the electric grid, and that ranged from doing research on renewable energy sources, how they're produced, energy demand, and factors that affect both of them. I also collected data from the grid, and I found reliable sources and websites to get that data from. The most reliable source I found was EIA.gov for the United States electric grid. So here is a EIA graph of the energy demand in the United States. So the light blue dotted line is the demand forecast. It's actually EIA's prediction of what the demand will be for the day, and that is put in at 10 a.m. every day. The darker blue line is the actual demand of the day, which is updated live, and then yellow is the net generation. So why is energy demand important? So for our project, we're looking to charge Zebra devices when renewable energy is the highest and non-renewable energy is the lowest. And natural gas is actually the biggest non-renewable source of energy. Actually follows the energy demand line very closely, as you can see from this next graph that I will show you. So this is the same day, and these two peaks mimic the energy demand line pretty closely, and I've just highlighted this data point here to show you as an example of when a good time to charge during the day would be for Zebra devices. So non-renewable energy is low is pretty low, and then solar energy is at its peak at the same time. And we also plan on displaying this data on our dashboard so that consumers can understand why their printers are charging when they are, and also just to have the energy grid data readily available to them.
My name is Eddie Perez, and I'm a computer engineer working on Project Amelia, and my primary focus for working on the project was to work on the Bluetooth capabilities of the system, alongside assisting with some of the memory components of our design, and programming some of the microprocessor elements. So to start, one of the first things I had to do was decide which Bluetooth manufacturer we were going to use in our design. I put some research into weighing the different pros and cons of different manufacturers against each other, such as the IDE they use for development or the different tools available for debugging, and ultimately we decided that Nordic Semiconductor would be our manufacturer of choice for our design, in part due to a personal recommendation from one of our technical directors, but also because of the vast amount of resources they allowed developers to have to ease us into their tool sets. In addition, I put some research into the different device roles in Bluetooth Low Energy, in particular the differences between broadcaster peripherals and typical peripherals, and the decision between this came down to whether or not we wanted Project Amelia to function as a broadcaster that just sends out packets of data to random devices that are willing to listen to it, or if it should be capable of making a dedicated bidirectional communication to an external device that is capable of sending information to and from. And ultimately we decided that making Project Amelia a typical peripheral will align more closely with our anticipated best outcomes. But we also had some discussions where, if we have the time, we can implement some kind of broadcaster functionalities should we feel the need. In addition, I created a custom Bluetooth Low Energy service from scratch. Services in Bluetooth Low Energy dictate how data is passed between devices by packaging them up as characteristics that hold values and send them out over Bluetooth. So for the sake of Project Amelia, I created a custom service that just has a couple baseline components, 2 characteristics that can read data and send that out. So I was successful in implementing a baseline service. And in addition, I put some research into learning how non-volatile storage functions within a Nordic system on chip. In particular, I learned how reading and writing from memory functions, and I used that knowledge to implement read functions into one of the Bluetooth Low Energy custom service characteristics, where the characteristic, when it is called to send data out via Bluetooth, it'll read whatever data element is stored in memory and broadcast that element out. So I was successful in integrating non-volatile storage and our Bluetooth Low Energy implementation. Here is just a high-level view of the Bluetooth functionalities of our system, where you can see that the Bluetooth Low Energy system will read and write from memory, and when it is time to broadcast an element out via Bluetooth, it'll read that element from non-volatile storage and send that out to an external application that is capable of reading and interpreting that data.
My name is Andrew Wu, and I'm a computer engineering major working on this project. My focus is on grid data, the cloud, Wi-Fi, and the microprocessor. So Microsoft Azure was the chosen cloud service for this project, and I set up multiple services within Azure, such as the Internet of Things hub and storage account, which would be used for connecting devices to the cloud, as well as storing data. I assisted connecting the microprocessor to the cloud by configuring all the necessary settings within Azure, and gathered the necessary security information to implement in the code for the microprocessor to get a secure, stable connection to the cloud. Device data routing was also implemented, as the data was sent to the IoT hub and then configured to be routed to the storage account to be stored and viewed at any time. I also conducted real-time web scraping with a Python program I wrote that gathers the renewable energy mix in the power grid to check when it will be at its peak in order to use less fossil fuels as a power source and reduce the cost of charging. And work on the dashboard was also conducted in order for users to visibly see when the best time for charging would be. So in this block diagram, the device to the left is sending MQTT messages to the Azure IoT Hub, and once they are received, those messages are sent off to message processing. Now within the Azure IoT Hub, there is a device manager, and it is configured to have a secure, stable connection with the device in order to allow the device to send messages and data. In this block diagram, there's a web scrape application, and once it runs, it sends a request to the data source, and it sends back a response with the necessary information that was requested. And once the extraction is completed, the data is sent off to data storage to be viewed at any time. And all of this work between the cloud server and web scraping application is important because it informs the user how they can maximize the use of green energy, reduce the use of fossil fuels as a power source, and reduce the cost of charging.
Hello, I'm Alan. I'm one of the computer engineers on this project, and I am responsible for the microprocessor memory, the watchdog timer, and the real-time clock. For my individual tasks, I was responsible for the non-volatile memory, which is the microprocessor flash memory for the NRF 5340DK board, and the memory will be used to store summations of energy consumed by the Amelia Power Platform in periodic timestamps, the renewable energy ratio, the charge enable status, and other information that will be accessed by Bluetooth and uploaded to the cloud. I was also responsible for selecting the external flash memory chip to be used in the event that additional memory storage is needed. The watchdog timer is used to reset the subsystem microprocessor in the event of malfunction, and the real-time clock is used to keep track of the current time and date independently of the main system clock. And finally, I was tasked with the green energy mix, where I conducted research on electric grids and the ratio between renewable and non-renewable energy in regions of California. So on the left is a graphic representation of how a watchdog timer operates. A timer is utilized to count down to 0, and if the timer reaches 0 without being reset by the microprocessor, the system will assume that something is not functioning properly and initiate a reset to correct the latch up. On the right is a block diagram of the real-time clock, which is going to have a separate power source to maintain accurate time even in the event of a power disconnection, as visible by the battery on the right. And this is to be used in the Amelia subsystem for time-dependent information being stored in memory, such as the power consumption and charge times. So finally, I have a basic block diagram of how the non-volatile flash memory will be manipulated. Thus far, we have basic code to erase a sector in flash memory, and we will verify if the erase was a success. Then we will write to memory, and finally read from memory at that memory location to verify if the data matches the values that were written.
I'm Nick Fedorenko, and I'm the electrical and computer engineering double major working on this project. My focus is establishing Wi-Fi connectivity between the microprocessor and the cloud server. My technical responsibilities include selecting and integrating the Wi-Fi chip into the subsystem, establishing the MQTT messaging protocol between the board and the cloud, developing firmware for the microcontroller, and assisting with cloud configuration. MQTT was selected as the messaging protocol for our project due to its lightweight nature, ideal for constrained IoT devices with limited bandwidth and resources, its low power usage, which is essential for battery-operated IoT devices. MQTT also supports two-way communication, which can be used to send messages between the board and the cloud. Lastly, its scalability. MQTT can support the integration of thousands of devices simultaneously. For the project, we decided to use a thin client approach. This means that all the computation happens in the cloud, and we just send a simple charge enable signal over MQTT to start charging the device. The device also sends battery information to the cloud in a neat JSON format, which the cloud stores and presents in a user-friendly dashboard. Our future technical accomplishments that we aim to achieve include establishing a working Wi-Fi MQTT code, developing web scraping code for the live grid data, creating schematic diagrams and a PCB layout for our board, then soldering and testing said board. We also aim to merge our Wi-Fi, Bluetooth Low Energy, and memory management codes into one program, develop a web app for battery analytics, enhance our Bluetooth service, and lastly, integrate a watchdog timer and clock into the board. For our key acknowledgements, first of all, we would like to thank our technical directors Joe Morera and Bradley Willard for giving us their time and guidance by providing us information and aid in order to achieve the best possible outcomes for this project. We would also like to express our heartfelt gratitude to Dr. Sunak for providing us with this incredible real-world opportunity to collaborate with Zebra Technologies. This experience has truly given us a taste of what it's like to work as engineers in the field. We're so grateful for this valuable learning experience. Thank you.